Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on quadratic forms. So basically everything we've looked at up until now has been linear. Now we're going to look at something that's quadratic. So a quadratic form is an expression of the form Qx, where x is a vector, x transpose AX. Now, because of their nice properties, we actually want A to be a symmetric matrix, because this will mean it's orthogonally diagonalizable, as we've seen, but also all its eigenvalues will be real. So let's look at an example. So if I have x and A as written here, then x transpose AX is calculated as follows. Now, it turns out if we go ahead and do the calculations, we end up with this quadratic form, x1 squared minus 8x1x2 minus 5x2 squared. So this is a quadratic in two variables, x1 and x2. So note the link between the entries in the matrix and the quadratic form. So this turned out to be the coefficient of x1, this is the coefficient of x2, and the coefficients of the cross term, x1 times x2, it's halved here and here, half of -8. So if the matrix is symmetric, then those off-diagonal elements will both be the same, and they are equal to half the coefficient of the cross term. So this is a quadratic form. Now we're interested in the minimum and maximum value that this quadratic form can take. So I'm about to rub out what's on the bottom of this screen. Please pause and copy down if you need. So this is our quadratic form in red. Now what we can actually do is we can perform a change of variable. X equals py, or if you like, y equals p inverse x for some invertible matrix P. But we're going to choose the matrix P in the right way. That's going to make this quadratic form a lot easier to handle. Now, because A is symmetric, as I said before, and as you've seen in previous lessons, it's orthogonally diagonalizable. We can write A equals PDP inverse for some orthogonal matrix P and diagonal matrix D. So our quadratic form was x transpose AX. That's just a normal quadratic form. But if I change x for py, I can write it like this. And then, of course, I can use the rules of transposition. Remember, you switch the order to get y transpose p transpose APY, like this. So this is a quadratic form. Instead of like the matrix A, we have this matrix here. Now you can make this substitution, that's fine. All this is a change of basis or a change of variable. So when we write x, whatever it is, the vector x, we sort of assume that it's using the basis 1, 0, and 0, 1. But instead, y sort of uses the basis, whatever the columns of P are. It's just using a different basis. So this is fine, this change of variable. But we don't want to just use any invertible P. As I said, we want to take advantage of this fact here. Now, because A is symmetric, it's orthogonally diagonalizable. So remember, an orthogonal matrix, its transpose is its inverse. So we want to pick P such that A is equal to PDP transpose, where P transpose is the inverse of P. So if we pre-multiply by P transpose and then post-multiply by P, we actually get that P transpose AP is equal to D. And as I said, D is a diagonal matrix. Now you can do this for any symmetric matrix. There will exist matrices P and D that satisfy this. So that means our quadratic form will reduce to Y transpose dy, where D is a diagonal matrix. And if this is a diagonal matrix, it means we won't have these terms here, so there won't be any cross product terms. So let's actually see this by diagonalizing A. So remember, what we have to do is first find its eigenvalues and eigenvectors. Now, because we've had so much practice at this, I'm just going to go ahead and do it without stepping it out. So these are the two eigenvalues and their associated eigenvectors. And as I said, it turns out for a symmetric matrix, you always get real eigenvalues, and they're always linearly independent eigenvectors because A is always diagonalizable. Now, when we're setting up P a unitary or an orthogonal matrix, we need to make sure its columns are unit vectors. So we need to just find a unit eigenvector. Its length is 1. So we just divide by the square root of 2 squared plus 1 squared, or root 5. So similarly for the second one, we need to divide each entry by root 5. It's still a scalar multiple of V, so it's still an eigenvector, but its length is 1. So now we can set up our matrices P and D as required. So remember, we set up P so its columns are the eigenvectors of A. Again, you can always do this with a symmetric matrix. We have D is a diagonal matrix whose diagonal entries are the eigenvalues of A. Now, because the first column of P was V1, lambda 1 needs to go here and lambda 2 here. Okay, and of course P inverse is just the transpose of P. And you can, if you want to convince yourself, show that P times D times P transpose equals A. So what we have here is that we can write our quadratic form X transpose AX like this. So it's YT times this matrix 3, 0, 0, minus 7 times Y. So here Y is just going to be the change of variable. It's just going to be Y1, Y2. So our quadratic form actually becomes this. So this quadratic form obviously has no cross product term, and it's easier to deal with. Now, sometimes we want to know the maximum and minimum of a quadratic form. So it would be hard to do if there was a cross product term. Now, there is no overall minimum and maximum because Y1 and Y2 thus far, they can be as large as we want. But what we usually do is we give some conditions to the vectors. Usually we have conditions like norm of x equals 1. Note that that's exactly the same as saying x transpose x is equal to 1. That's saying that they have to be unit vectors. And similarly here, we might say that y has to have length 1 and be a unit vector. So if y has to be a unit vector, the minimum and maximum are really easy to see. The maximum would occur when y1 is equal to 1 and y2 is equal to 0. The maximum value of this quadratic form is 3, and the minimum value of this quadratic form is minus 7. Again, that's subject to the constraint that y has to be a unit vector. So this highlights something very interesting that didn't just happen by chance at all. Note that 3 and negative 7 are the eigenvalues of our original matrix A. So it turns out for a quadratic form subjected to the constraint that the vectors have to be unit vectors, it turns out the maximum value of the quadratic form is the largest eigenvalue and the minimum is the smallest eigenvalue. And although I spent a while just going through why things work and setting it up, this is a really easy and quick way of finding minima and maxima that doesn't involve calculus. Alright, so let's now take a look at a 3 by 3 matrix for a quadratic form. So let's say we have this quadratic form that now has 3 variables. Let's set up the matrix of this quadratic form A. So we know it's going to be a 3 by 3 matrix. If there are n variables, then we have an n by n matrix. So along the diagonal go the coefficients of the terms that are not cross terms. So the 1 entry is the coefficient of x1 squared is 4, the 2 entry is the coefficient of x2 squared, and the 3 entry the coefficient of x3 squared. So what goes here at the 1, 2, and 1 entry, we halve the coefficient of x1, x2. So in this case, it'll be -1 and -1. So similarly, here and here, the 1, 3, and 3, 1 entries are half the coefficient x1, x3. So we are going to put a 3 there. Now, because there's no x2, x3 cross term, we just put zeros there. Again, we want to set up A so that it's symmetric, so that we can take advantage of its nice properties. So if I go ahead and calculate the eigenvalues of this matrix, I need an eigenvalue calculator because it turns out to be pretty tricky, I get this. These are the 3 eigenvalues that I get. So what that means is, if I say that I have the vector x1, x2, and x3, that's my vector x, and if I say that x has length 1, this is the maximum value I can get, and this is the minimum value I can get of this quadratic. Once again, that's subject to this constraint, which is the same as saying that the square root of x1 squared plus x2 squared plus x3 squared is equal to 1. So if I substitute in 3 values for x1, x2, x3 such that this is equal to 1, the maximum value of this expression is going to be just over 6, and the minimum value just under 0.9. So to actually find what vector I would substitute, what values for x1, x2, and x3 I substitute, all you need to do is find the unit eigenvectors corresponding to that. So to find the values x1, x2, x3 that make it a minimum, I find the unit eigenvector corresponding to this. That will give me the 3 entries, and the unit eigenvector corresponding to this eigenvalue will tell me the values of x1, x2, and x3 to make this expression a maximum. All right, we just have to go through a few definitions and then we're done. So here are some definitions we need to know. Note that the blues correspond to each other. So in the first definition, it's saying that Q and A are both said to be positive definite if all eigenvalues of A are greater than 0, and Q and A are positive semi-definite if all eigenvalues of A are greater than or equal to 0. It makes sense to say that the quadratic is positive definite and also that the matrix is positive definite. So in the second one, it's saying Q and A are negative definite if all eigenvalues of A are less than 0, and semi-definite if all eigenvalues of A are less than or equal to 0. Now, if A has some positive, some negative eigenvalues, then we say it's indefinite. So remember, the lowest eigenvalue gave the minimum of the quadratic, and the highest eigenvalue, the maximum of the quadratic form, subject to the vector having length 1. So of course, if all eigenvalues of A are positive, then the quadratic form can only take on positive values. Similarly, if all eigenvalues of A are negative, the quadratic form can only take on negative values. And if A is indefinite, it means the quadratic can take on both positive and negative values. You know, just like a parabola. Sometimes there are always positive values of y, sometimes always negative, sometimes both. In general, it's not easy to look at a matrix and determine whether it's positive or negative definite or semi-definite, or whether it's indefinite. You know, you might have a matrix that has all positive values, but it could have a negative eigenvalue and be indefinite. We just don't know from looking at it. Of course, some matrices, it's really easy to tell. Remember that diagonal and triangular matrices display their eigenvalues along their trace, along the leading diagonal. So you could absolutely tell for those ones, but in general, this isn't easy to do. I want to also stress again that A is a symmetric matrix. If A is not a symmetric matrix, remember, some of the stuff I've told you in this video won't work, like that you can diagonalize it, for example. So A has to be symmetric, and then these definitions hold. All right, thank you so much for watching this video. This has been the luckiest maths teacher in the world. Have a great day.